Hello, my Calc 2 student. We continue our lecture. Today, now I covered section 5.2, natural logarithmic function integration. Okay, how you remember what's coming from definition of our logarithmic function? You can easily see this is theorem. Oh, sorry, it's not working. Okay, theorem tell us integral 1 over x dx. It will be natural logarithm x. And second one is, okay, you have in the book this 1 second, but I not see, this is very big difference, 1 over u. The u, it will be natural logarithm u. Okay, my mistake, plus c here. This is absolute value and plus c there. Okay. Second coming because we have du, it will be exactly u prime dx, and use this fact and use how we found derivative of our logarithmic function, we can prove these formulas. Okay, doing some examples. Example A, very simple example. What happened if you have 5 over x dx? Remember, you can take it all coefficient out of your integral. It will be 5 dx over x. It will be 5 natural log absolute value x plus c. B, what happened if you have something a little bit more complicated? It will be 3x squared plus 1 over x cubed plus x dx. How looking for this this function who stay inside integral and see relation between numerical and determinant. You have, if you x cubed plus x, we substitute like u, take a derivative, it will be exactly 3x squared plus 1 dx, it will be du. And this means you have du over u, or you have a natural log. Well, let's go u, absolute value u, this means natural log, absolute value x cubed plus x, and then plus c. Okay, move our scale. Doing one more example. It's work, it's not only if you have some algebraic function. For example, I have integral secant square x over tangent x dx. Between numerical and determinant, you have same relation. If you have tangent x, it will be u. Then derivative tangent, this will be secant square x. We have differential, this means secant square x dx, it will be du. It means you have natural log absolute value tangent x plus c. Don't forget about this coefficient. Doing something little bit more interesting, some example where it's a little bit harder. For example, I have integral when I have some x squared plus x plus 1 over x squared plus 1 dx. Here you need to remember about long division, because we can divide our numerical by our determinant. Okay, doing long division, it can be a little bit easier, but okay. I'm divided by x squared plus 1, and result 1. Give me x squared plus 1. Subtract, we have x is remainder. This means my my integral here, I write this star and I continue there. It will be integral 1 plus x over x squared plus 1, and this is dx. First term is no problem. Second term, we're doing some x plus, okay, I'll write one more time, x over x squared plus 1 dx. If we x squared plus 1, let's go, it's u, then 2x dx, oops, dx, it will be du. Looks like I need 2 here. Okay, I write 2, this means I write 1/2 there, and then it's nothing changing because I cannot multiply it by 2 when I want. Okay, and finally we have x plus natural log x squared plus 1. How you see, I'm not use absolute value here because x squared plus 1 is always positive. This means we don't need any absolute value. Plus c. We're solving this example too. One more question, one more example. Now I give you so much examples because this couple of sections we need practice, and I am try cover it more type of exemption, so what you can do in yourself is homework. Okay, next example. It will be 2x over x plus 1 square dx. Looks like I need some substitution here because I don't see how I can do it. Okay, here I'm doing this way. X plus 1, I'm plugging like my variable, new variable u. Then you can see easy axis will be u minus 1, and the x is exactly du. Oops. And we have now twice u minus 1, because its x is u minus 1, divided by u squared du. Separate for two fractions and simplify. If you have twice integral 1 over u minus 1 over u squared, oops, du, give me twice natural logarithm absolute value u plus 1 over u plus c, or we every time when you're doing substitution, don't forget go back with your old variable, because it's new variable, it's only help us. Twice natural log absolute value x plus 1 plus 1 over x plus 1 and plus c. And now, how you remember, we can find derivative for all our 6 trigonometrical function, but it's not true for integrals. We try found some integrals for some trigonometrical function and see how it's work. For example, integral from tangent x dx. Remember definition, tangent is sine over cosine. Remember relation between sine and cosine. This means I'm doing substitution. Cosine x, it's some u. Derivative, it will be minus sine x dx. It will be du. And now I have minus integral du over u will give me minus natural logarithm absolute value u plus c, or minus natural log absolute value cosine x plus. See, we prove some formula. Integral from tangent x equal this kind of function. See one more example. Integral from secant x dx. Here we need a little bit more complicated. I'm doing this way. I have some function secant x, and then I multiplied and divide for something same. This means multiplied and divide for secant x plus tangent x. If I multiplied and divide for something same, is nothing changing. This means I'm not changing anything. But, okay, rewrite one more time, it's more. Now my numerical is secant square x plus secant x tangent x. And my denominator is still secant x plus tangent x dx. Now I try use u substitution. This means secant x plus tangent x. Let's go, it will be u. Take a derivative. What is derivative secant? Is product secant tangent, right? Secant x times tangent x. What is derivative tangent? Is secant square x. Multiplied by dx, it will be du. But if you see for your integral, it's exactly your numerical. This means here we have, continue, we have natural log from secant x plus tangent x plus c. Use absolutely same technique. Okay. You can prove this fact. Integral from cotangent x dx will be natural log absolute value sine x plus c, and integral from cosecant x. What I'm right, sorry. Oh my god. Cosecant x dx will be minus natural log absolute value cosecant x plus cotangent x plus c. And now we prove, and we have a formula for integration all our 6 elementary trigonometrical elementary functions. Now I give you a couple of examples from your book as something similar from your homework. For example, number 18 is from section 5.2. Here you have, inside integral, you have rational function x cubed minus 6x minus 20 over x plus 5 and dx. Here you can use long division or synthetic division, your choice, and divide your numerical for your determinant, because you see power is determinant is 1, you have linear there, and this is you have x cubed, this means power is much more. Okay, here we divide x cubed minus 6x minus 20. Okay, I'm using long division, x plus 5. You have chance for remember x cubed. How I need multiplied x for be x cubed? I think it's x squared. This is I have x cubed plus 5x squared. Subtract negative 5x squared minus 6x. I need multiplied by negative 5x. Negative 5x square. 5 times 5, it will be negative 25, I think, minus 25x. Subtract, you have 19x minus 20. Here you multiply, this will be 19. Okay, it will be 19x, and 19 times 5, it will be 95, plus 95. Subtract, it will be minus 150. Okay, this means after division you have integral. When you have result your integration, it will be x squared minus 5. Oops. 5x plus 19 and minus 115 over x plus 5. And all of them is dx. How I can write dx? Okay. It's not perfect, but I hope. Now I clear this part. I can move, but I think it's clear here. It will be work better. And it will be equal x cubed over 3 minus 5x squared over 2 plus 19x, and here we have minus 115, natural log absolute value x plus 5. Oops. Plus c. Okay, one more similar for your homework is number 24. What happened if you have dx over x to the power 2/3 1 plus x to the power 1/3? Well, I think you can see what kind of substitution we have. We write 1 plus x to the power 1/3. Let's go, it will be u. Then take a derivative, it will be 1/3 x to the power 1/3 minus 1 is negative 2/3 dx, it will be du. Great. This means we need dx divided by x power 2/3, but we have exactly this part, right? We need 1/3 here. This means I need 3 there, and I write 3 here. This is help me. And now my integral I can rewrite like 3 integral du over u. It will be 3 natural log absolute value u plus c will give me 3 natural log absolute value 1 plus x to the power 1/3 plus c. Okay, and one more example. Example number 28. 28. I give you number, it's from your textbook. Okay, it will be integral 1 over 1 plus square root 3x dx. Well, here we whole denominator substitute with new variable 1 plus square root 3x. It will be u. take a derivative, it will be 1/2 whole 3x is negative 1/2 power times derivative 3x will be 3, and then as dx, it will be du. Okay, great. What does mean? I need in the denominator, okay, 3 halves, no problem. This means I write, okay, I'm write equal different color. I write what I multiplied, divide, when you can see how it's changing. I have 3 halves inside integral. This means I write 2/3 out, integral 3 halves. Then I have what I had before, 1 plus square root of 3x, right? But I need square root of 3x in the denominator, square root of 3x here. Oops, this is we proof. I promise you use different color when you can see how it's changing. Okay, square root of 3x here, and this means I write square root of 3x there because I cannot write what I want only. Okay, and dx. You see what we multiplied and divided, how changing our integral. Now we go to new variable. All coefficient and dx over root, it gives us du. Great. This means now we have 2/3, but square root of 3x in numerical, it will be u minus 1, then du, divide by u. You see? Now we can solving, because what we have here, it will be 2/3 integral 1 minus 1 over u du. Oops. It will be equal 2/3 u minus ln absolute value u plus c. And if you remember what is u was, what we have here, it's 2/3 u is square root of 1 plus square root of 3x minus natural log 1 plus square root of 3x. Here I not use absolute value because I think it's x is positive. This means square root of 3x positive, and this means add 1 is positive, and plus c. We did. Before we continue solving, I want to give you some theorem who make our life much easier, because we're always happy if something make it our life is much easier. Then is this kind of theorem. And so, if integral your function fx dx equal big fx plus c, then integral, whereas f is have linear combination ax plus b dx equal 1 over a f ax plus b, oops, plus b, I want to be here plus c. Okay, first we prove this theorem, especially we don't have in the book this theorem. Let's go evaluate this integral. Integral f ax plus b dx. Use substitution ax plus b like u. This a dx will be du. This means your integral, it will be 1 over a f from u du. Give you 1 over a big F from u plus c, and go back with your old variable. It will be 1 over a f from ax plus b plus c. Okay, say some example. How it's help you this theorem. Example. Example A. Let's go. We have integral from tangent 5x dx. How you remember, integral from tangent is minus natural logarithm integral from cosine. Because we have coefficient 5 here, this means you have 1/5 natural log. Oh, oops, sorry, I forgot about minus. Minus put in the here. Absolute value cosine 5x plus c. You see, now we're ready for write this integral. B. What has happened if you have dx over 3x plus 4? Remember, this is linear combination. A is 3. This means here I have 1/3 natural log 3x plus 4 absolute value plus c. Okay, and one more example. What happened? And we need to remember what is defined in find integral. For example, I have integral from pi over 8 to pi over 4 cosecants 2 theta minus cotangent 2 theta d theta. Well, here good, we have coefficient 2, both of them. Integral from cosecant is give me natural log cosecant plus cotangent, but because we have 2 here, this means we have minus 1/2 natural log absolute value cosecant 2 theta plus cotangent 2 theta. Here we have, because minus cotangent, you have minus natural log absolute value, oops, sine 2 theta. 2 theta. And here we need plugging border from pi over 8 to pi over 4. Plug, and we have, okay, cosecant pi over 2, it will be 0. Cotangent pi, just a moment. Cosecant, it will be 1. Cotangent, it will be 0. This means here I have minus 1/2 natural log 1. Then I plug in pi over 4 from sine, and then I have minus natural log, oops, here we have one more mistake, 1/2 here. Okay, 1/2 natural log 1. Then we plug in pi over 8 and we subtract. This means we have plus 1/2 natural log. It will be square root of 2 plus 1 plus 1/2 natural log square root of 2 over 2. Remember, natural log 1 is 0, and final our answer, oops, final our answer will be 1/2 ln square root of 2 plus 1 times square root of 2 over 2. It will be 1/2 ln 2 plus square root of 2 over 2. I think it's good enough. Okay. Or maybe one more example. Define integral. Integral from 0 to 1 x minus 1 over x plus 1 dx. Well, here, because we have very good coefficient, I'm add 1, subtract 1, and I have finally 0 to 1 1 minus 2 over x plus 1 dx equal x minus twice natural log x plus 1, and all of them 0 to 1. We counting, we have 1 minus twice natural log 2. If you plug 0, we have minus 0 plus 2 natural log 1, who is 0. Finally, I have 1 minus 2 natural log 2. Okay. Okay, guys, this is what I want to tell you about section 5.2. If you have any question about homework, please send me email, and we make it, and I'm trying to answer it for all of them. Remember, we have office time on Tuesday. It's it. Oops.